facilitate this difference. I'll also just point out that if you do go to your assignments, there are now new biography project, citizen science, open-ended projects that specify that they're for earning points for the Stellar Science badge, and those will just be due on the 22nd when the badge ends, when the test is. There's also a new homework assignment similar to this last one, but focused on what we'll be covering here. And I do think the first question on this now, see how easy it is for me to pull this up. It's not easy. Can I just view it? No. Okay. The first question, though, is really focused on hydrogen atom stuff. So if you do want to take a look at that, that first one is longer, but it will be one that you have all the knowledge to do. I'm also planning on making a video again about your labs, so I will let you know about those. I'll put that out soon. I'll make this one available over 4-day, but these first 3 are all about measuring light. This one we haven't quite talked about yet, but it takes a little extra work. You have to go somewhere with a view. So if you are going somewhere with a view over 4-day, might be worth checking this one out. Otherwise, this one needs that diffraction grading. So if you haven't gotten your lab equipment yet, this one will have to wait. And then this one is just, you can do it anywhere as long as you have a smartphone. Cool. So then there are, again, just like last time, there are reading questions that are showing up as we move through our material. So, anyone have any questions about anything before we jump into the sun? Not literally. And I promise we will eventually save the astronauts, just probably not today. The astronauts will still be there. We will be able to save them next class, next week after 4-day. So today we're going to start talking about the sun. This is kind of our introduction to stars, has to start with the sun because the sun is our closest star. We use the sun to figure out a lot about the other stars that we will look at, just because we have way more information about the sun than any other star. So the sun is about 8 light minutes away. So light from the sun takes about 8 minutes to get to us. The next closest star is about 4 light years away. So that's kind of our comparison. The closest star is 4 light years away, so that light will take 4 years to get to us. Because stars are for the most part so far away, we can't actually resolve the surfaces of other stars. So what that means is when we look at the sun, we can actually kind of take images where you can see individual features on the sun. We can see spots, we can see bright places, we can see other things, and we can really measure what's going on the sun. Every other star is so far away that when you take a picture of it, the star is going to be smaller than even the best pixels on the best cameras we have. So we can't actually see individual features on those stars. We can just use how they look compared to the sun to get information on them. Little side note, just to kind of try to put this in perspective. So last year, there was a big to-do in astronomy because we had our first image of a supermassive black hole. And the reason why that was so impressive was because of the resolution idea. So black holes they're huge, but because they're so far away, they take up a very small area on the sky. So taking a picture of that supermassive black hole that was so far away was similar to if you took a picture of a donut on the surface of the moon. So if you imagine having a camera good enough that if you had a donut on the moon, like a normal donut, and you somehow got it to the moon, you could take a picture of the moon and actually resolve that donut, which is hard to do. And in order to do that with this black hole, we needed a telescope the size of the entire Earth. So we had to use multiple telescopes all over the Earth to create one big telescope. And that's how we were able to do that. So we've done that with black holes. Haven't really done that yet with any stars because stars emit at different wavelengths, which just makes it more difficult. So this is a long way to say this is why we're starting. We're going to start really digging into the sun because the sun is our baseline for figuring out other information about stars. We can use what we know about the sun to make to figure out what's happening on other stars. So hopefully you figured out by now that I'm never going to expect you to memorize numbers because I think that's silly, but these are just some little basic facts about the sun taken from your textbook. What I really like about this chart from your textbook is they also tell you how all these different measurements were completed. So a lot of these are also things that we've already done. So they're things that you could do if I gave you the proper data and the right pushes. So I just want to say, you guys are all astronomers. You're doing great. And these are all measurements that, yeah, you guys could do. You have all the knowledge to do. So for example, we find the distance to the sun from Earth by bouncing radar off of nearby planets like Venus and Mercury. So we can figure out how far away Venus and Mercury are. We can look at how long it takes Venus and Mercury to go around the sun. And we can use the ratio of a year on Venus and a year on Earth and that distance between them, along with Kepler's laws, to say Kepler's third law, to figure out what the actual distance between the Earth and the sun is. So it's just a Kepler's law argument to figure out the distance to the sun using kind of ratios of orbital periods of the Earth and the other planets. You can find the mass of the sun by using just the law of gravity. So we look at how long it takes the Earth to go around the sun, how far away it is from the sun, and you can actually get a mass. If you've done the composition of Saturn lab, you have done this with Saturn. So this is another thing that you all could do. The composition of Saturn lab is one of the ones that's actually, I reopened for this section. So if you do want to still do that one, you can. So if you want to find out how we can find the mass of planets, but also the mass of our sun, you can see how you can use the laws of gravity to do this. And we find that the sun is about 300,000 times the mass of Earth, which is crazy. It's huge compared to Earth. And then there's some other measurements here, the angular size, the mean angular diameter. So that's how much angular space does the sun take up on the sky. So the entire sky, if you look from horizon all the way up to the other horizon, that would be 180 degrees. The sun is about half a degree. So don't look at the sun, but if you did, it would take up about half a degree on the sky. That's also similar if you fully extend your arm. Your thumbnail is also about half a degree. The full moon is also about half a degree. So that's 31 arc minutes. 30 is half of 60. There are 60 arc minutes in a degree. You can then figure out the diameter of the sun the same way, again, in this composition of Saturn lab, the same way you did to find the diameter of Saturn by using the angular size and the distance and just a little bit of trig. And we find that it's about 100 times the size of Earth. So 300,000 times the mass, 100 times the distance across. Other cool things to point out here, the luminosity of the sun, so the total energy, that light energy we talked about before, is 3.8 times 10 to the 26th watts. Normal light bulbs are about 15 to a couple hundred watts. So light bulbs in our house are about 10 to the 24th times fainter than the sun. They put out 10 to the 24th less energy than the sun. We'll talk more about spectral classes later. The temperature of the surface of the sun you can find using Wien's law and the spectra of the sun. So that's another thing y'all could do if I gave you the right data. And what we've found is that it's about 5,800 Kelvin or about 10,000 degrees Fahrenheit. So this is the temperature of the surface of the sun, which there's not really a surface, but the outer layers, I guess I should say. So those are just, again, some basic facts, but I just wanted to point out that, show you how we measure these things, and also point out that you guys could all make most of these measurements and get this data with, yeah, like I said, just a few pushes from me. You have this knowledge. You're astronomers. You're doing it. Sorry. I get excited about doing science, maybe obviously. Okay. Today we're going to talk mostly about the outer layers of the sun, but I wanted to start just by briefly mentioning the inner layers as well. Unlike the Earth, we separate the sun into layers just like we do on the Earth, but unlike the Earth, those layers don't correspond to differences in composition. They instead correspond to differences in temperature and how energy is transported. So pretty much all of the sun is hydrogen. It's about 90% hydrogen by number of particles, and then about 70% hydrogen by mass. So 70% of the sun's mass is hydrogen. And then most of the rest of it is helium, with a little bit of other heavier elements. So for astronomers, there's hydrogen, helium, everything else is we call metals. So the sun is mostly hydrogen and helium just because those are the most prevalent elements in the universe. They're also the lightest two elements. So hydrogen's 1 proton, helium's 2 protons. And we'll play with that a little bit more when we look at how energy is generated in the sun. The core of the sun is the very center. It's where nuclear fusion is happening, and it's where energy is generated. So again, we'll talk about this more later. Right outside of that, things are really hot, and energy is transported through radiation, which is just light traveling. So if you have a heat lamp, maybe you have a pet turtle, and you have a heat lamp for that turtle, that heat lamp is transferring energy through radiation. It's transferring heat energy through radiation to your turtle to keep him warm. So in this layer of the sun, energy is transported through radiation. In the outer layers, instead of radiation, energy is transported through convection. Convection is similar to if you boil water to make hot chocolate or coffee or something, tasty warm beverage, when that water is boiling, it is moving energy through convection. So there's the hot stove, water at the bottom gets hot and it starts to rise. As it rises, it cools slightly and it falls back down. And as that water bubbles and moves up and down, heats, cools, it transfers energy until all of your water is at a boiling temperature. So that's what convection is. It's this kind of flow, transfer of energy through boiling, essentially. So the outer layer on the sun is kind of the convective zone. It's where energy is moved through convection. So we have our core where nuclear fusion is happening, radiative zone where energy is transferred through radiation, and then convection zone where energy is transferred through convection. Another little kind of cool thing, the reason we know what's happening inside of the sun is kind of similar to how we know what's happening inside of the Earth. So on the Earth, we use seismology. We used earthquakes to figure out the different layers. We can sort of do the same thing on the sun. The sun does not have plate tectonics, but the sun does experience quakes. So we can see ripples, waves, sunquakes on the surface of the sun, and we can actually observe those to figure out what's happening inside of the sun. So just like we use earthquakes to find out what's happening inside the Earth, we can use sunquakes to figure out what's happening inside of the sun. So it's kind of a brief overview of the inner layers. Today we're going to focus more on the outer layers. So looking at the corona, the photosphere, which is what we can see, and then the chromosphere, which is kind of the layer between. Any questions there? There's a whole branch of science called astroseismology, which is like starquakes. It's just studying quakes on other stars. It's hard to do though. You can mostly just do it with the sun. Okay. So those were the inner layers. Like I said, though, today we're going to focus more on the layers of the atmosphere. Because those are the layers we know more about. We cannot go inside of the sun. We can just learn a little bit based on those sunquakes and also how energy is coming out of the sun, the energy we measure from the sun. So the layers we're going to focus on instead are the photosphere, which is the layer that we see, the chromosphere, which is the layer right above that, and if you use the right sort of telescope, you can look at the chromosphere, and then also the corona, which is the outer layer of very hot, very low density gas. So we can only really see the corona during solar eclipses. So if you did see that 2017 eclipse, when the moon was totally blocking the sun, if you saw some light emanating around it, that would have been the solar corona. We're going to start with the surface. Again, this is surface in quotes because the sun doesn't really have a surface like we might think on the Earth. Similar to kind of when we talked about the gas giants, sort of, there's whether or not there's a solid surface. There's definitely not a solid surface on the sun. All of it is plasma. So we talk instead about the photosphere, which is the depth we see into the sun. So it's the layer in which light escapes and actually reaches us. The layers inside of this are just, there's so many free electrons that are just absorbing light and scattering light, absorbing light and scattering light. And so that light does not escape the inner layers of the sun. It just gets kind of bounced around by the electrons inside those layers. So the photosphere is where we can start to actually see photons no longer get absorbed and scattered by free electrons. They actually escape and they fly off towards us. And so that's the deepest we can see. It has that temperature of 5,800 Kelvin or 10,000 degrees Fahrenheit. And it's about 100 kilometers thick. And it's but only, even at 100 kilometers thick, it's only about 1/7,000th the radius of the sun. Even though it's just a really small layer of the sun, we can learn quite a bit from the photosphere based on all these kind of different features we see on the photosphere, different changes. So things like, we'll talk about granules and limb darkening, and then also sunspots, but all those things can tell us a lot about what's happening inside of the sun. We can also use spectra of the sun. When we look at a spectra of the sun, we're looking at the spectra of the photosphere. So that's telling us what the sun's photosphere is made of. It's also telling us what the temperature of that photosphere is. Sunspots and flares that we see on the surface also tell us a bit about the magnetic field of the sun, which is crazy to think about. So the first thing I said is that we can use, we can look at the photosphere and we can use limb darkening to get a bit of an idea of what's happening at different layers. So limb darkening is just that the outer edge of the sun is going to look slightly fainter than the inner parts. Again, don't look at the sun, don't look at the sun, don't look at the sun. That is not good for you. But when we take pictures of the sun using very special telescopes, we can see that the inner parts look brighter and more yellow, and then the outer edge looks oranger and dimmer. And that's because we're seeing into different depths into the sun. So when you look directly into the center, you're seeing down, the base of the photosphere that you're seeing down into is going to be a different thickness. And you're going to see a different depth. So this is kind of similar to if you look through the horizon at the edge versus if you look straight up. So if the sun's at the edge of the horizon, you're looking through more atmosphere. And a lot of times it might look redder. It's why we see pretty sunsets. Where while it's at the top of the atmosphere, it's coming through less atmosphere and we just see the sun as a small dot. But if you can think the same thing is happening with the sun when we're looking at the edges, we're not seeing down as deep into the sun, we're seeing kind of through the edge of the sun. So we're getting an idea of what's happening in those different parts of the atmosphere, of the photosphere, I should say, sorry, different amounts of that 100 kilometers. So limb darkening tells us a little bit about what's happening in the very outer layers of the sun. Because we're seeing to different depths. If we look right in the center, we're seeing deeper. As you look at the outer edges, you're seeing further in. Also mentioned how we can use granules to look at what's happening inside of the sun. And specifically, this is how we know the outer layer of the sun is moving heat through convection. So this is a video of the sun, and what we can see is that there's kind of these. It looks almost like a lava lamp or something, but you can see it's sort of boiling up to the surface. So the hot middle parts of granules are the hot things that just rose. As they cool, they kind of split apart, they get to be a darker color, and that cooler material falls back down. So hot rising gas, and then cool sinking gas. And this is how we know that there's that conductive layer at the surface of the sun, or near the surface of the sun. Some other little kind of fun facts. Granules are about 1,000 kilometers across, so fairly large, kind of crazy to think about, even though when you look at how many there are on the sun, each one is 1,000 kilometers across. And the motion of the plasma inside of these granules is so fast that it breaks the local speed of sound. So they're moving 15,000 miles per hour. So there's all these kind of, if you somehow were at the surface of the sun, you would be hearing all of these sonic booms from these granules moving as the heat was transported, energy was transported up. So kind of crazy to think about, but we can use, again, we're looking at the photosphere, we're seeing these granules, and that tells us that there must be a layer in the sun where energy is transported through radiation, or through convection, sorry, convection, because it looks like boiling. I could keep my words right. Any questions so far? Sorry, today's a lot of information. Another thing we see on the surface of the sun is sunspots. So sunspots are the darker areas on the surface of the sun where magnetic field lines from the sun have gotten kind of twisted up and they have held material there. So the sun, since the sun has all of these charged particles, it's flowing charged particles, there's a ton of magnetic fields. Magnetic fields happen whenever you have flowing charges. Moving charges create magnetic fields. So the sun is a bunch of electrons, a bunch of ionized hydrogen, so protons and electrons, charged particles, they're all flowing, so we get just a bunch of magnetic fields. When those magnetic fields get tangled, they can hold the charged material at the surface, allowing it to cool down from that 5,800 to around 4,500 Kelvin instead. So again, not cold according to Earth temperatures, but cold compared to the surface of the sun. And so they look darker. If it wasn't for the fact that they were right next to the sun, these would shine very brightly, but because they're next to this extremely bright sun, they look dark. So convection is prevented by magnetic fields. The magnetic fields of the sun are about 5,000 times stronger than those of Earth. So they can hold these materials and we get these dark spots. So just showing this, the sunspots happen where the magnetic field bursts through the surface due to the kind of motion of both the rotation of the sun and the motion of the gas, and they prevent convection, they stop things from falling down, so we get especially cool spots that look darker than the rest of the surface. Another cool thing we can do with sunspot is we can measure how fast the sun is rotating. So we can look for the same sunspot, and as long as they're there for at least one rotation, we can get a measurement of the rotational time for the sun. So like what a day would be on the sun. It's a little weird to think about because everywhere is getting sunlight on the sun. But that's kind of the equivalent on Earth. One rotation is one day. And one thing that scientists have noted is that the rotation in period is different if you're on the equator or if you're at a pole on the sun. And this is because the sun is not a solid body, it's a big ball of plasma. So it's kind of all liquid-ish, so you get kind of sloshing around, and the rotation at the equator is faster than the rotation at the poles. So at the equator, things are moving, a rotational period is about 25 days, where at the pole it's about 35 days. So the sun isn't really a fixed, perfect sphere. It's kind of all liquid plasma sloshing around. Because of that, this tangles the magnetic field lines more. So you start with your kind of nice straight magnetic field lines, the differential rotation at the equator and the poles kind of smears them all together and causes more sunspots to occur. So that's what this is trying to show. We start with nice aligned magnetic field lines, the differential rotation smears them out, and we end up with something that's kind of messy for a certain period. And during that period, there's a lot of solar activity. So that smearing, because of that differential rotation, leads to something we call the sunspot cycle. So there's kind of peak in activity of sunspots every 11 years. So we can count the number of sunspots. This is another thing you'll do in that sun lab. And what we see is that every 11 years, there's kind of a peak in the number of sunspots. So we can see that there was a peak, I think, in 2014. So we're about to start increasing as we move. We fill in this plot, but hasn't quite gotten to 2020 yet. But so we're going to start entering a period of solar maximum as we move forward. In addition to this 11-year, so we're not 100% sure why this cycle occurs, but we think it has something to do with the smearing of magnetic field lines. Kind of a fun thing with the planets, when we didn't know why something happened, we threw a collision at it. With stars, when we don't know why something happens, we throw magnetic fields at it. So that's kind of, I don't know, probably magnetic fields. Yeah. So that could be why we see this 11-year cycle, but it's not 100% clear. In addition to this normal 11-year cycle, back in the 1600s, there was something called the Maunder minimum, where there was a period of about 60 years where there were very few sunspots. It was also the same time as the Little Ice Age. So there was a little ice age where things cooled down a bit, but this is probably not related. So there less sunspots don't mean ice age. It's probably correlation, not causation. But we did see back in the 1650s, they noticed there was a very long period of time where there was fewer sunspots than you would expect. So in addition to the small granules, there are also kind of giant super granules. So the granules were those boiling bubbles. Those were 1,000 kilometers apart. These are about 3,500 kilometers apart. They last longer and they carry the magnetic fields. So the main thing, this is kind of an image showing that where we're seeing red is things that are falling down, blue is things that are moving up. So that's kind of trying to show these bigger granules on the surface of the sun. This also has to do, but it's more thinking the super granules move the magnetic field lines of the sun. So that's the important thing here. So that's the photosphere. That's our first layer. Our surface was the photosphere. We use the granules to show that there must be convection happening on the layer beneath them. We can take spectra of that layer to find temperatures as well as composition of that layer. The sunspots tell us about the magnetic fields where they're getting trapped. And they also tell us about the rotation of the sun. So those are some of the things we can learn from the photosphere. Before we get into the chromosphere, does anyone have any questions about the photosphere? Okay. And like I said, if you did like learning about that, the Sun Lab would be a good one for you because you get to explore more about the photosphere. The next layer above the photosphere is the chromosphere. It's called the chromosphere because of its nice red color. So chrome has to do with color, the Greek word for color, I believe. So chromosphere, colorful sphere. And it's very red. It was first observed during solar eclipses, where people would see a kind of small red circle as the moon covered up the sun, but usually we can't observe it because what we're instead of seeing is the photosphere. Temperatures are actually higher in this layer than they are in the photosphere. And the temperature rises quite quickly as you move through the chromosphere. So starting at the photosphere at about 6,000 degrees Celsius, moving up to about 20,000 degrees Celsius as we get into the corona. And that's just how energy is transported, and there's also lower density, so it's easier to get things moving faster, get things to higher temperature. The red color is caused by the presence of hydrogen, so we usually see it in red just because there's a lot of hydrogen, again 70% by mass, 90% by particle, and that red is that longest wavelength of hydrogen. So it's a visible emission line, so we can see it even if there were some of those Lyman alpha, that 10.2 electron volt transition that you saw in your activity last week, we wouldn't observe that because that would be in the ultraviolet. So we see the H alpha, we see the 1.9 electron volt emission. A lot of the solar activity occurs really in this layer. So when I say solar activity, I'm going to talk about space weather. We're going to get into that probably more after 4-day when we have to save the astronauts from some space weather, but it's happening kind of in this layer at depths of 3,000 to 5,000 kilometers. And I think I said this earlier, but it's a very low density in this layer, so 10 to the -4 times as dense as the photosphere, and that's the Earth is 10 to the 8th time, so about 10 to the 9 is a billion. So the Earth's atmosphere is about 100 million times denser than the chromosphere. So our atmosphere is 100 million times denser than this outer layer on the sun. So very, very low densities compared to what we're used to. We can talk about, just like we used features of the photosphere to study the sun, we can look at the chromospheric network, which is the kind of web-like patterns we observe in the chromosphere that outline the position of the supergranules and teach us more about the magnetic fields. So like I said, the magnetic fields were created by the supergranules. So looking at where they are, where they're outlined by these lighter web-like patterns in the chromosphere, we can figure out how magnetic fields are traveling through the sun. This will just say really quickly, this image is purple instead of red because instead of looking at that hydrogen emission, this was a filter that was specifically looking at a transition in calcium. So singly ionized calcium is what the Ca2 means. So the sun also has quite a bit of calcium in its atmosphere, so we can also look at this calcium transition to get an idea of what's happening in the chromosphere. So this is another kind of spectra help us tell us what's happening inside of stars, or what elements are present. In the sun, we know there's quite a bit of calcium. This is, again, we're back to that red, so we're back looking at H alpha. So neutral hydrogen, 656 nanometers, or 6,563 angstroms. Sorry. Hammer home how important spectra is again and again. But we can also look for filaments and plages in the sun's chromosphere. So filaments are these little kind of funky lines, and then plages are the darker areas. And they're all, again, kind of similar to the sunspots on the photosphere. These are areas where the magnetic field lines are holding material present, allowing things to cool instead of fall back down and get heated up again by the hot core of the sun, energy coming from the core of the sun. oh, sorry, I think I misspoke. Filaments are the darker spots. Plages are these lighter spots here, sorry. And they surround sunspots where the filaments are darker, more similar to the sunspot. So you're going to get bright areas right around the sunspot where material is a lot hotter than the sunspot itself. We also see prominences inside of the chromosphere, which are kind of dense clouds of material. So clouds in the sun are going to look like prominences. They are stuck in magnetic field lines. So again, we're really focused on these magnetic field lines, but we can use the observation of these prominences to find out how the magnetic fields are coming in and out of the sun. So material that gets kind of pulled out by the magnetic field lines from the sun. This one here is the granddaddy prominence. So in 1946, we saw a very large prominence explode from the sun. So these are all kind of trapped still. We're not getting explosions out. This is just happening on the surface of the sun. We're seeing these kind of big loops of cloud material, big loops of plasma that are erupting from the surface of the sun and are being held in the magnetic field lines that are also bursting through the surface of the sun. Sort of similar, there are also some just instead of loops, there are just jets that come out of the chromosphere called spicules. They appear as darker streaks, again, because they're going to be cooler, because they're escaping, they're moving out, they're not being pulled back down towards the hot material in the core. And these are where we're starting to get into some of the space weather. So the sun is ejecting material into space at high speeds, so 20 to 30 kilometers per second, or about 44,000 miles per hour. And those can reach Earth. It's why we're seeing some aurora in Walla Walla right now. There's a lot, the sun is blasting out a lot of energetic particles, and some of those are hitting Earth's atmosphere and causing the oxygen in Earth's atmosphere to emit that nice green light. Yeah, so the spicules are just, instead of loops, they're just kind of jets that come straight out. So that's the chromosphere. Any questions about any of that? Again, we can take spectra of the chromosphere to find that it has a lot of hydrogen as well as some calcium and other elements. We can use the spectra also to find the temperature and see how the temperature is changing as you move out of the sun. And then a lot of the activity in the chromosphere tells us about the magnetic fields of the sun, which can also teach us about what's happening inside. So the next layer between the chromosphere and the corona is called the transition region. It's a thin region where the temperature changes rapidly from about the 20,000 degrees Celsius at the edge of the chromosphere to about 1,000,000 degrees Celsius in the corona. It's pretty difficult to observe because hydrogen in this layer is completely ionized. So all the hydrogen is just protons. There are no electrons to shift between energy levels. So we're not getting those same absorption lines. So the hydrogen no longer has electrons. So if there's no electron, it's just a proton. There's nothing to move between energy levels. So we can't use spectra to find hydrogen there, because in a lot of ways, there's not hydrogen, there's protons and electrons. Instead, we look at singly ionized carbon and oxygen. So even though the carbon and oxygen may have lost one electron, they still have quite a few left. Carbon has 12 electrons and 12 protons. Oxygen has 16 electrons and 16 protons. So even if they've lost one, they still have a lot left to move between energy levels. And we can use those to measure this layer that doesn't have any hydrogen left. From that, again, we can get kind of temperatures and some idea of composition. But we just know that this is a very thin layer, low density, again, similar to the chromosphere that had that density 10 to the minus eighth times the density of Earth's atmosphere. And we're rapidly changing from really hot to really, 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 really hot. So the corona is then that next layer that is extremely hot, but extremely low density. So as I said, the next layer is the corona. We're not going to spend much time on the transition layer just because there's not a lot to look at there. The corona we can pretty much only measure, we can only see during solar eclipses, so when the sun is blocked out by the moon, or if you are on a space telescope or some other sort of high altitude observatory, and you can put a chromosphere on your sun to block the sunlight. So the sun is so much brighter than the corona that anytime you try to look at the corona, you can't see it because all you're seeing is the sunlight. So this would be like if you were out at night and you were trying to see a firefly next to a stadium light. You wouldn't see the firefly because all you would see was the light from the stadium light, like the football stadium light or something. But when the moon very nicely slips in and blocks the light from the sun during solar eclipses, the sunlight is blocked, obviously, and we can see the corona for that brief moment of time. Like I said, it's extremely hot, so it gets up to about 1,000,000 degrees Celsius, but it's very, very, very low density, so even lower density than the chromosphere. So there was like what my astronomy professor, Andrea, the other astronomy professor here, used to say, if you dipped your hand in a bucket of corona, your hand would freeze because of the low density. So even though it's really hot, there's nothing really there. So the way we think about temperature is kind of you need an atmosphere to feel a temperature. So you need material to get a temperature. So because there's so little material, even though the material that's there is very high temperature, we wouldn't experience it that way. It extends millions of kilometers out into space from the surface of the sun, so kind of shoots off really far, extends way out from the surface of the sun. And it's created by charged particles moving in the sun's magnetic field. So as the magnetic field from the sun pulls electrons, ionizes hydrogen, you can accelerate those electrons and protons up as they spiral around the magnetic field lines, and you can get just really high temperatures in this coronal layer. This is also where a lot of solar weather is kind of, again, coming from, is material getting shot out along the magnetic field lines in the sun through the corona. And so one of those ways you might see that is through helmet streamers. So these are the large structures that are observable in the corona, and they usually occur above sunspots, other places where the magnetic field lines are getting twisted up. So whenever there are loops of magnetic fields, maybe there would be a prominence down here in the chromosphere, maybe there would be a sunspot on the photosphere. You get a density in charged particles spiraling around the magnetic field lines. So magnetic fields attract charged particles, so there's just slightly higher density here, and we can observe it as brighter helmet streamers around the sun. This is also where solar flares happen. So similar, instead of just streaking straight out in those helmet streamers, we get kind of loops of charged particles moving along magnetic field lines. And they are called coronal loops because they are in the corona, and they are loops along the magnetic field lines. And they can cause solar flares. So when we talk about solar flares, they're caused by charged particles moving through the corona. So it is 12:49. Sorry, I've talked for a long time today, but I wanted to make sure we finished up the light and got through a lot of this solar material. So you have all submitted your responses to this. We will save the astronauts after 4-day from coronal mass ejections. And I think good news is I'm going to be able to take out one of the more math heavy activities that we were going to do next week. So positive. And I will try to put out some information on the labs if you want to tackle any of those over break. And I will be available on that Zoom link tonight if anyone wants to work on maybe the sun lab or the measuring light lab, the other two, or the inverse square law lab, the other two require getting outside a